Okay, we're in Physical Chemistry, Chapter 10. We're in Section 6 now. We're going to talk about solutions of electrolytes. Now, a true electrolyte is when it exists as ions in the pure state, which means they don't technically have molecules. Example is sodium chloride or potassium iodide or lithium fluoride. There's no such thing as a molecule of sodium chloride. The solid is just alternating NaCl, NaCl, etc. Then there's also potential electrolytes. Potential electrolytes are actually uncharged molecules when they're in the pure state. For example, let's say we have CHCOOH in water. It reacts to form these ions like this. Or likewise HCl plus water that'll form hydronium ions and the chloride ions. So it acts kind of like an electrolyte, even though it was a molecule before it was dissolved. So the formula is usually the metal and then the non-metal. So so this is the formula, like nu is the subscript for the positive, the metal, and then the negative. So remember, this is not mole fraction. This means metal and non-metal, like the hydrogen, chlorine, and so on. Now let's talk about true electrolytes. Then we have the metal and the nu plus, and then the non-metal and the nu minus in the solid state. Then that's going to go to the metal, and how many of them depends on the subscript. So if it had 3 of them, then it'd be 3 of those. If there'd be just 1 of them, there'd be 1 of them, etc. And then the X is going to, like whatever the subscript here was, if it was 3, then we'll have 3 of those. If it was 2, we'll have 2 of those, etc. And then it's going to have a charge. The metal will have the Z plus charge, and then the non-metal will have the Z minus charge. So the nu plus and nu minus are obviously integers, and that's, like I said, the subscripts. For example, let's say we have barium nitrate. Notice there's 2 nitrate ions for each barium. So our metal here is barium. The non-metal here is the nitrate ion. The mu plus, or nu plus, is 1 because there's 1 barium. The nu minus is 2 because there were 2 of these nitrates. And then the charge on the barium is going to be 2. And then the Z minus will be minus 1 because each nitrate will only have minus 1 charge in the solution. Here's an example of a potential electrolyte. This is calcium phosphate, I think. So the metal here is calcium, and then the non-metal here is the phosphate ion. So the mu3, or the nu plus, there's 3 of them, and then the mu minus, there's 2 of them. So the Z plus, that's going to be 2 because the calcium ion is going to have a plus 2 charge. And then the Z minus will be minus 3 because each phosphate will have a minus 3 charge. Now, if we have a Z plus equals 1 and a Z minus, absolute value of Z minus is equal to 1, then we have what we call a 1-to-1 electrolyte. Now the calcium phosphate is a 2-to-3 electrolyte because the Z plus is 2 and the absolute value of Z minus is 3. So calcium nitrate is going to go to the calcium 2 plus ion and then 2 of the nitrate ions. Oops. Now, so we have calcium 2 plus and the nitrate is minus. That can mix to make a calcium nitrate plus. So this is what we call an ion pair. The more concentrated the solution is, the more likely we are to have ion pairs. Now let's talk about chemical potentials in electrolyte solutions. So again, we have this MX electrolyte, metal, non-metal electrolyte. So we have the metal with a Z plus charge, and that is the chemical potential of the plus ion. And then we have our non-metal with the Z minus charge. That's our chemical potential, the minus ion. And then remember, I showed you before how we can have a metal with the X, Z plus, plus a Z minus. So then we have the chemical potential of an ion pair. And then, of course, don't forget, we still have the solvent, which is the chemical potential of the substance A. Obviously, we wouldn't have a solution if we didn't have a solvent. So we have the chemical potential of the positive is going to be defined as the partial derivative of the Gibbs free energy with respect to the number of moles of the positive at whatever temperature, pressure, and then all the other moles held constant. So remember, N is the number of moles of the electrolyte, and then N is fixed. So neither the chemical potential of the plus or the chemical potential of the minus can actually be measured. Now we do have the chemical potential of substance I is the chemical potential of the electrolyte. So the chemical potential of the substance I is defined as the partial derivative of the Gibbs free energy with respect to the number of moles of the actual electrolyte at temperature, pressure, and holding the number of moles of the solvent constant. Now mu is actually measurable. And of course I is our electrolyte, the solute. Okay, we're going to have a named equation here, which means we want to be able to refer back to it later on. So we have equation 1, the differential of the Gibbs free energy is equal to minus the entropy times the differential of temperature plus the volume times the differential of pressure plus the chemical potential of the solvent times the differential of the number of moles of the solvent plus the chemical potential of the positive electrolyte times the number of the differential of the number of moles of the positive electrolyte plus the chemical potential of the minus electrolyte times the differential of the number of moles of the negative electrolyte plus the chemical potential of the ion pairs times the differential of the number of moles of the ion pairs. Now if no ion pairs form, then we have the metal, and then that's the nu plus, and the non-metal, and the nu minus. And then N plus will be equal to nu plus times the number of moles of the substance I, the solute. And then the N minus will be equal to the nu minus times the number of moles of the solute. So remember, N minus is the number of moles of the anion, and then N plus is the number of moles of the cation. Now, if ion pairs form, then the number of moles of the positive, the cation, is equal to the nu times the number of moles of the substance I minus the number of moles of the ion pairs. And likewise, the number of moles of the anion will be equal to this nu minus times the number of moles of the substance I minus the number of moles of the ion pairs. Now we want to take the differential. So we get the differential of the number of moles of the cation is equal to the nu plus times the differential of the number of moles of the solute minus the differential of the number of moles of the ion pairs. And likewise, the differential of the number of moles of the anion is equal to nu minus times the differential of the number of moles of the solute minus the differential of the number of moles of the ion pairs. Now we want to take these two equations and substitute them back up into equation 1. So what we get is the differential of the Gibbs free energy is equal to minus the entropy times the differential of temperature plus the volume times the differential of pressure plus the chemical potential of the solvent times the differential of the number of moles of the solvent plus the chemical potential of the cation times this whole quantity here, the nu plus times the differential of the number of moles of the substance I minus the differential of the number of moles of the ion pairs plus the chemical potential of the anions times this whole quantity, the nu minus times the differential of the number of moles of the substance I minus the differential of the number of moles of the ion pairs, and then plus the chemical potential of the ion pairs times the differential of the number of moles of the ion pairs. Now remember, the chemical potential of the ion pairs is just going to be equal to nu plus the chemical potential of the plus the chemical potential of the minus. Or that's for one ion pair. So we can substitute that up here. So we get the differential of the Gibbs free energy is equal to minus the entropy times the differential of temperature plus volume times the differential of pressure plus the chemical potential of the substance A times the differential of the number of moles of substance A plus the differential of the number of moles of the solute times this whole quantity, the chemical potential of the cation times the nu of the cation, plus the chemical potential of the anion times the nu of the cation, anion, minus the chemical potential of the cation times the differential of the number of moles of the ion pairs, minus the chemical potential of the minus times the differential of the number of moles of the ion pairs, plus the chemical potential of the plus times the differential of the number of moles of the ion pairs, plus the chemical potential of the minus times the differential of the number of moles of the ion pairs. Now we can simplify by combining some like terms. So we get the differential is minus, or the differential of the Gibbs free energy is equal to minus the entropy times the differential of temperature plus volume times the differential of pressure plus the chemical potential of the solvent times the differential of the number of moles of substance A, the solvent, plus the differential of the number of moles of substance I, the solute, times this whole quantity, the chemical potential of the plus times the nu plus the chemical potential of minus times nu minus. Now we're going to set constant temperature and pressure. Therefore those dt will be equal to 0 and dp will be equal to 0. So the dg is just going to be equal to that last term. The differential of the number of moles of substance I times the chemical potential of the cation times the nu of the cation plus the chemical potential of the anion times the nu of the anion. So we get the differential of the Gibbs free energy is equal to the differential of the number of moles of substance I times the chemical potential of substance I, since we can substitute in like we did before. Therefore, the chemical potential of the substance I is equal to the chemical potential of the cations times the nu of the cations plus the chemical potential of the anions times the nu of the anions. This is an important equation. So for example, let's say we have sodium chloride. Then the chemical potential of the sodium chloride aqueous is equal to the chemical potential of the sodium plus when it's aqueous plus the chemical potential of the chloride when it's aqueous. Now notice calcium chloride, you have 2 here for the nu, so we get the chemical potential of the calcium chloride when it's aqueous is equal to the chemical potential of the calcium 2 plus ion when it's aqueous plus 2 times the chemical potential of the chloride ion when it's aqueous. Now the chemical potential of the substance I is equal to the chemical potential of the cation times the nu of the cation plus the chemical potential minus times the nu of the anion. Now remember, the chemical potential of the solvent is equal to the chemical potential of the solvent in the pure state at whatever temperature and pressure plus the gas constant R times the temperature times the natural log of the gamma times the mole frac of X sub A times X sub A. So remember, G sub I is the mole fraction activity coefficient of the solvent. And remember, activity of the I is equal to gamma I times chi I. Now we want to express this, though, in terms of molality. Then we get, so M plus, that's the molality of the cation, of the metal Z plus. M minus is the molality of the anion of the metal Z minus, or the non-metal Z minus, so they changed that. So gamma plus is the molality of the molality scale activity coefficient, and then gamma minus is going to be the molality scale activity coefficient of the cation anion. So we get the chemical potential of the cation is equal to the chemical potential of the cation in the standard state plus the gas constant R times the absolute temperature times the natural log of this whole quantity, the molality scale activity coefficient of the cation times the molality of the cation divided by the molality in the standard state. And of course the molality of the standard state would be 1 mole per kilogram, and that's kilogram of solvent. And of course gamma has no units. Then we have the chemical potential of the anion is going to be equal to the chemical potential of the anion in the standard state, plus the gas constant R times the temperature times the natural log of the molality scale activity coefficient for the anion times the molality of the anion divided by the M0, which is the standard state, molality. Then we have the gamma, or activity, of the cation at infinity means infinite dilution, which basically means there's almost zero in the substance, in the solution. So the gamma, the activity coefficient at infinite dilution, is equal to 1. Then the chemical potential I is going to be equal to the nu plus times the chemical potential plus the nu minus times the chemical potential minus, cation, anion. So the chemical potential I is going to be equal to the chemical potential I times the this is nu, mu, plus nu RT ln gamma molality divided by standard molality. So this will be for the cation, and then the same thing for the anion, because you just put them together. And then you can factor out, and you get the gamma times molality times molality. Notice they pulled the exponent into, oh no, that was in here. Yeah, you pulled this into the exponent. So you have to the nu plus power and to the nu minus power. Now these individual quantities can't be measured, but the gamma plus to the nu plus times the gamma minus to the nu minus is measurable. So we're going to define an activity coefficient for plus or minus. This will be the molality scale mean ionic activity coefficient. So you're going to say that the gamma plus or minus to the nu plus nu minus power is just going to be equal to the nu plus to the, or the gamma plus to the nu plus power, times the gamma minus to the nu minus power. There should be a minus sign. That's ugly. That's if you have one or more electrolytes. So this is just a way of simplifying all the different electrolytes in one solution. Let's do an example here. So let's say we have barium chloride. So it's going to be 1, 2, 3, or 2 and 1 is 3. So we have gamma plus minus to the third power is going to be equal to the activity for the cation to the first power times the activity for the anion to the second power. So you solve for this, the gamma plus minus, and you'll get gamma plus to the first power times gamma minus to the second power, then take all that, the cube root, the 1/3 power. Now let's say we have chemical potential of substance I is equal to the chemical potential I in the standard state plus R times T times the natural log of the gamma plus minus to the nu times the molality of the cation divided by the molality of the standard state, or that times to the nu plus power, times the molality of the anion divided by the molality of the standard state to the nu minus power. And remember, nu we got just by adding nu plus nu minus. So add up all the numbers. Now remember, the molality of the substance I is the number of moles of the solute divided by the mass of the solvent in kilograms. Now let's assume we have no ion pairing. Then we're going to get the substance M nu plus times the mole fraction nu minus. That's going to become the nu plus the cations and the nu minus the anions. In other words, it dissociates when it gets dissolved. So we get nu plus is equal, or no, the molality of the cation is going to be equal to nu plus times the molality of the solute. Solute. And then the molality of the anions is going to be equal to the exponent nu minus times the molality of the original substance. So we say that the molality plus and the molality minus are the ionic molality. So we get the molality of the cation to the nu plus power times the molality of the anion to the nu minus power. That's going to be equal to the nu plus times the molality of the substance I to the nu plus. And then the nu minus times the molality of I to the nu minus. See how we substituted that in. And then that's going to be equal to the nu plus to the nu plus times the nu minus to the nu minus times the molality of I times the nu. And remember, nu is equal to is defined as the nu plus the nu minus. So the overall coefficient is going to be the coefficient of the cations plus the coefficient of the anions. So that's just like when we had the gamma plus minus. When we said that gamma plus minus, those are supposed to, yeah. So now we have nu plus minus to the nu is defined as nu plus to the nu plus times nu minus to the nu minus. So let's say we have magnesium chloride. So it's 1, 2, 3 again. So we have nu plus minus to the third is equal to 1 to the 1 times 2 to the 2. So solving for that, we get nu plus minus is equal to the cube root of 4, or roughly 1.587. Then we have nu plus minus to the nu times the molality of the cation divided by the standard molality to the nu plus times the molality of the anion divided by the standard molality to the nu minus. And that's going to be equal to nu plus minus times gamma plus minus times the molality of I divided by the standard molality to the nu power. So we get the chemical potential of the substance I is equal to nu I naught, the standard state, plus, oh, that's mu. So the chemical potential of I is equal to the chemical potential I in the standard state plus nu times RT times natural log of nu plus minus times gamma plus minus times the molality of I divided by the standard molality. Now again, this assumes strong electrolytes and no ion pairing. Okay, that is the end of Chapter 10, Section 6.